Hello, my name is Professor Douglas Feynman. I'm a professor in the Nuclear Engineering Department at UNIST. And in today's lecture, it's for regression for scientists and engineers. In lecture 1, we'll go over some definitions and introductory concepts. So let's jump right into it. So first, let's go over some definitions. And I'm using actually the Merriam-Webster's Collegiate Dictionary, which is actually quite good if you're looking for a decent dictionary. And so the topic of this course is regression and regression models. And so regression, the root word is regress, which is a noun. And the definition of regress is the act of reasoning backward. There's also a verb form, which is to tend to approach or revert to a mean. So regress, the act of reasoning backwards, or alternatively in verb form, to tend to approach or revert to a mean. So there's reasoning backwards and reversion to means. Now the word regression is a noun, and there's actually two definitions. So the first definition is, for regression, is a functional relationship between two or more correlated variables that is often empirically determined from data and is used especially to predict values of one variable when given the values of the other. So a regression is a functional relationship between two or more variables. The alternative definition for regression is, number 2, is a function that yields the mean value of a random variable under the condition that one or more independent variables have specified values. So here, definition 1 for regression is a little bit broad or qualitative. It's just a functional relationship between two or more correlated variables. But a more precise definition, it's a function that yields the mean value of a random variable. Okay, so let's explore some of these key words. So empirical, what does empirical mean? Empirical is an adjective. Means originating in or based on observation or experience. So in other words, empirical is when we make observations about the natural world. And so empirical means it's not based on theory, physics, or first principles. So it's based on our observations. And so the first definition said it's a regression is a functional relation that is often empirically determined. So not always. So most of the time we do regressions based on the empirical evidence. But an important note is, but you can incorporate the underlying physics or theory into a regression model if known. So if you know something about the underlying physics of the research you're doing, you can incorporate that knowledge into regression models. So here are just some common examples. So for example, if you're a biologist and you're studying bacteria, the growth of bacteria colonies follows an exponential growth curve. And so if you're measuring time series data of the growth of bacteria, we know that this tends to be exponential. And also, there are sinusoidal patterns in environmental or weather measurements. And so if you're doing, for example, temperature measurements, we know that, for example, there's night and day. Temperature tends to be colder at night and hotter during the day. Also, if you're doing measurements over the whole year, there's winter, spring, summer, fall, which these seasons repeat year after year. So for certain environmental or weather measurements, we might want to think about, sine waves or cosines. Next, random variable. So a random variable is a variable that it it is itself a function of a result of a statistical experiment in which each outcome has a definite probability of occurrence. And so basically what we're trying to say here is that the experimental measurements are not exact, okay? And so there's many sources of error, or random error, or randomness in our measurements or our experimental observations. So for example, we always will have the precision of a measuring device. So for example, if let's say we have a scale to measure the weight of an object, if it's a digital scale, there's usually a number of decimal places on the scale. So the number of decimal places on the digital meter. Also, there's always static noise in electrical circuits. And we sometimes will call this type of noise white or white Gaussian noise, because this random noise in electrical circuits tend to be normally distributed. So we call it white or white Gaussian noise. Also, even if you go into quantum mechanics, there's the introduction of the concept of uncertainty. So the Heisenberg uncertainty principle basically gives the standard deviation of the uncertainty of x, which stands for the position, times the standard deviation of momentum, which is related to the velocity or the energy of a particle. It has to be greater than or equal to Planck's constant divided by 2. So even from the quantum mechanics, we can never actually know the position. We cannot know simultaneously the energy and the position of a particle. And so what we should always think about as scientists and engineers is that the things that we are measuring or observing, they're not exact values, okay? They actually, if we were to repeat these measurements, we will actually end up seeing a distribution of values, okay? So if you, as a scientist or engineer, are asked a question, you should provide a best estimate plus an uncertainty interval. Okay, if you're asked a question or you're providing a result, you should provide a best estimate plus an uncertainty interval, or alternatively a range of values, or what's called a confidence interval, okay? You can give values but with a degree of certainty or probability. And you would do this based on your level of knowledge of the subject at hand. And so you always want to provide this range of answers with the expectation that the true value or the true answer is contained within your interval. And so let me explain this with a example. And so let's say, I know some of you are probably students at Post-Tech. I'm a professor at UNIS. I have visited the Post-Tech campus maybe 3 or 4 times since around 2014. And so I am not an expert on Post-Tech, but I have visited the campus. And so if you ask me how many students are currently enrolled at Post-Tech, I really don't. I have a rough idea. So if you were to ask me how many students are enrolled at Post-Tech, I would assign an interval. I would say probably, I'm going to call my answer Y, probably greater than or equal to 1,000 and less than or equal to 15,000. Because I really don't know how many students are enrolled at Post-Tech. I suspect by visiting the campus, the number of buildings, and seeing some students probably greater than or equal to 1,000, but less than 15,000. Definitely, like 15,000 is a quite large university. I know UNIS, our Post-Tech, it's not a small university, but it's not a huge university. And so I'm just, this is quite a wide range, but it's based on my level of knowledge. Okay, so if you are if you've been a student at Post-Tech, or maybe if you work in the administration and you see enrollment data every year, you might be able to provide a much more precise answer. But also, I asked how many students are enrolled at post-tech. Is that the current enrollment? Is it the enrollment for the 2022, year 2022? Because, for example, during the semester, some students might drop out. And so the numbers of students enrolled at post-tech can actually change. And so even if you, say, worked in the administration at post-tech and you had the current data, 1 minute later, a student could decide to disenroll. And so our variables that we are measuring or observing, they're actually random variables. Okay, so it's really the result of the statistical experiment that is done at that point in time. And so let's just go back to the regression definition. It's a function that yields the mean value, or sometimes we call that the expectation value of a random variable, under the condition that one or more independent variables have specified values. Okay, and what about correlated variables y and x? And so the most simple case is what we call the bivariate case, where we have the variable y equals some function of x. Okay, y is some function of x, implying y is correlated to x. And so regression analysis aims to find or estimate the functional form of f that accurately describes the relationship between x and y. And so the relationship between y and x is derived from a set of n observations between x and y. And we call this set of n observations, we call this the data set. And we obtain this data set either from experimental measurements in the laboratory or out in the environment, or in many cases we might actually be obtaining this data from computer models or computer simulations. And so when I talk about regression and data sets, we can apply this both to computer-generated data, but also the experimentally measured data. And we can expand this to the multivariate case, where our dependent variable y equals some function of x, but x here is in boldface, meaning it's a vector. And so there are multiple input variables. So x1, x2, up to xn. And so that's the multivariate case. And generally, in this course, we're going to try to do all of our derivations for the multivariate case, because we can always then simplify to the bivariate case. Whereas sometimes on some of the textbooks and some of on the internet, a lot of times they only give the examples and derivation for the bivariate case. But especially when we go into the higher order relationships, you have a lot of what's called the variable interaction terms. And those can become very important when you have large input. Your input space has large dimensions. Okay, so the next concept is training and test sets. And so the data set that we actually use to create the regression model is called the training set. And so we're actually training the model on this data that we collected. And so, but when we do this, whenever possible, some of the data that you've collected should be left out of the training set to use for what's called cross-validation of the regression model. And so we want to leave some of our observations out of the data set so that when we've made this regression model, we want to be able to test its predictive accuracy. And by leaving some of the data out, this provides a blind check for the accuracy of the model, which we want to have an accurate model to make predictions. But also we want to identify, is there a bias? Is there any bias in our regression model? And also there's a major issue with regression. It's called overfitting, where the model is there's too much flexibility in the model and it fits to the random noise of the collected data. An overfit model generally gives very poor predictions. And so this subset of data that we leave out of the regression model training, we call this the test set or the cross-validation set. And so, but when we collect data, we usually will store these data in vectors or matrices. And so I'm going to use the bold capital Y is our vector. So it's going to be a column vector of our different output variables, y1, y2, yn-1, yn, our output variable observations. If it's a bivariate case, we can have the vector x, which is x1, x2, then to xn. So these are our different, the input variable values that we sampled during our experiment or computer simulations. But for the multivariate case, x is going to be a matrix. Okay, so and this goes back to the multivariate case. We have different variables. For example, if we're collecting data on a population of people, we might be measuring, for example, x1 might be their age, x2 might be their height, xn might be their weight. So we have different input parameters to our model. So we have our n observations of our first input variable, we have n observations of our second input variable, and then our nth input variable, we have our n observations. And so another thing you should get comfortable storing your data from either your computer simulations or from your physical experiment electronically. And this is where sometimes you can use like a spreadsheet like Microsoft Excel, but I would highly recommend, and there's going to be examples in this course, you need to learn a scientific computer programming language such as MATLAB or Python. And you should start storing this data in vectors and matrices within a scientific computing language program where you can then quickly manipulate that data and use that data in different calculations, including the regression model development. And so, for example, sometimes data sets can be extremely large. For example, this n, that might be 10 million. And there could be hundreds, if not thousands, of then individual input variables. And so these data sets can become very, very large. And so in software like Microsoft Excel, the program will crash if you're working with huge data sets. So you would need to be using a scientific computing language, such as MATLAB or Python. That way you can quickly and efficiently store, access, and manipulate your data set. And so we usually store data in vectors and matrices. Okay, next, let's go over some other terminology. So X and Y terminology. So we generally have our variables X and Y, but these are called, depending on the application or also the field of research, the different fields of research call these different things. For example, in a medical journals, they might be calling X and Y a certain thing, but then in a nuclear engineering journal, there's something totally different. So some common names for X is usually, the X is usually used as what's called the independent variable or our input parameter. Also our predictor or the explanatory variable. Also, they're sometimes called covariates. Also features. So these might be the features of the input space. Our Y is usually referred to as the dependent variable or the output or the criterion or outcome, the response or label. And there's probably also some other terminology to refer to X and Y. So generally in this course, we will use independent and dependent variable and input and output. But depending on what field of research you're in, they are sometimes called different things in the different applications. And now that we've had just some basic definitions and now we understand some of the terminology, let's go through the regression model hierarchy. Because now, especially with the advent of the personal computers, basically in the late 1980s, there's been an explosion of different regression methodologies in the past several decades. And so this is the way how I classify regression models. And so there are two major classes of regression models. There are the parametric regression and then the non-parametric regression. And so let's start with the parametric regression side. And so the parametric regression, we can further subdivide into linear models and nonlinear models. And by far the linear regression models probably account for well over 80% of the regressions that have been performed historically since the 1800s. Probably I'm guessing at least 70 to 80% of all regressions have been linear models. And so the linear models, the most common are the polynomial fits, which are based actually on the Taylor series expansion concept. We also have spline models, and there can also be something called weighted linear least squares. And so linear least squares regression is a type of regression that gives you a linear model. Now, for nonlinear models, this is where we incorporate nonlinear functions into the model. So usually we might be using exponential functions or logarithms, and also, for example, Fourier series expansion using sines and cosines. These are all examples of nonlinear models. But what makes it a nonlinear model and for the exponential function example, the rate and the frequency parameters. So frequency parameters in Fourier series expansion, if these parameters are being estimated from the regression, then it's a nonlinear model. And we're going to give a more specific example shortly. And also what's called the weighted nonlinear least squares is a type of nonlinear regression method. And so within parametric regression, we have linear models and nonlinear models, and then there are different subcategories of these linear and nonlinear models. So next let's move to the non-parametric regression. And so the non-parametric regression includes what I call a whole class of algorithms called data smooths or data smoothing. And most of the AI and machine learning, so nowadays the artificial intelligent AI and machine learning are these kind of popular buzz phrase used in research nowadays. I personally do not like the terminology AI machine learning. I tend to classify almost all of these algorithms as generalized, multivariate, non-parametric regression. And most of the AI machine learnings are actually data smooths. And so some specific examples would be the alternating conditional expectation or ACE algorithm, also Gaussian process model, the GPM, probably for the machine learning, probably over 50% of the machine learning applications are using the Gaussian process model or Gaussian process regressions. Also the artificial neural networks, the ANNs, they also fall under this AI machine learning. I consider both the GPM and the ANNs, these are data smooths. But one thing about all of these data smooths, AI and machine learning algorithms, they might employ both linear and nonlinear methods within the structure of these non-parametric models. And so especially some of these methods will apply a linear model in an input subspace. And so there is some interaction between the parametric regression and non-parametric regression.